welcome back to Neetopedia, that is Neetka Encyclopedia, and we are back with physics audiobooks of the chapter Alternating Current. Please note that we have already finished electromagnetic induction, EM waves, and modern physics including semiconductor electronics in our previous sections. Please check it out in the physics audiobook playlist on our channel. So without wasting time, let's begin. Chapter 7 Alternating Current. 7.1 Introduction. We have so far considered the direct current DC sources and circuits with DC sources. These currents do not change direction with time, but voltages and current that vary with time are very common. The electric main supply in our homes and offices is a voltage that varies with sine function with time. Such a voltage is called alternating voltage or AC voltage, and the current driven by it in a circuit is called the alternating current. Today, most of the electrical devices require AC voltage. This is mainly because most of the electrical energy sold by power companies is transmitted and distributed as alternating current. The main reason for preferring use of AC voltage over DC voltage is that AC voltages can be easily and efficiently converted from one voltage to the other by means of transformers. Further, electrical energy can also be transmitted economically over long distances. AC circuits exhibit characteristics which are exploited in many devices for daily use. For example, whenever we tune our radio to a favorite station, we are taking advantage of a special property of AC circuits, one of many that you will study in this chapter. 7.2 AC voltage applied to a resistor. Figure 7.1 shows a resistor connected to a source E of AC voltage. The symbol for an AC source in a circuit is in the diagram. We consider a source which produces sinusoidally varying potential difference across its terminals. This potential difference is also called AC voltage, will be given by V is equal to Vm sin omega t, where Vm is the amplitude of oscillating potential and difference omega is its angular frequency. To find the value of current through the resistor, we apply Kirchhoff's loop rule, where summation of all the voltages is equal to 0. To the circuit shown in figure 7.1, to get Vm sin omega t is equal to IR, or I is equal to Vm upon R sin omega t. Since R is a constant, we can write this equation as I is equal to Im sin omega t, where amplitude Im is given by Im is equal to Vm upon R. This equation is Ohm's law, which for resistors works equally well for both AC and DC voltages. The voltage across a pure resistor for the current through it is given by the equation and are plotted as a function of time. Note in particular that both V and I reach 0, minimum and maximum places at the time. Since clearly the voltage and current are in phase with each other, we see that the applied voltage, the current varies sinusoidally and has corresponding positive and negative values during each cycle. Thus, the sum of instantaneous current values over one complete cycle is 0 and the average current is 0. The fact that the average current is 0, however, does not mean that the average power consumed is 0 and there is no dissipation of electrical energy. As you know, Joule heating is given by I square R and depends upon I square, which is always positive whether I is positive or negative and not on I. Thus, there is Joule heating and the dissipation of electrical energy when an AC current passes through a resistor. The instantaneous power dissipated by the resistor is P equals to I square R, which is equal to Im square R sin omega square t. Sin square omega t. The average value of P over a cycle is P is equal to magnitude of I square R, which is equal to the magnitude of Im square R sin square omega t, where the bar over the letter denotes its average value and the brackets denotes taking the average of the quantity inside the bracket. Since Im square and R are constant, P is equal to Im square R sin square omega t. Using the trigonometric identity, sin square omega t is equal to 1 by 2 1 minus cos 2 omega t, where we have sin square omega t equals to 1 by 2 1 minus cos 2 omega t. Since cos 2 omega t is equal to 0, we have sin square omega t equals to 1 by 2. Thus, P is equal to 1 by 2 Im square R. To express the AC power in the same form as DC power, a special value of current is defined to be used. It is called root mean square or effective current. and is denoted by IRMS or I. It is defined by I is equal to I square under root. In terms of I, the average power denoted by P is P equals to half Im square R, which is equal to I square R. Similarly, we define the RMS voltage or effective voltage by V is equal to Vm upon root 2, which is equal to 0.707 Vm. Thus, Vm equals to IMR or Vm upon root 2 is equal to Im upon root 2R or V equals to IR. The equation thus gives the relation between the AC current and AC voltage, and it is similar to that in the DC case. This shows that the advantage of introducing the concept of RMS values. In terms of RMS values, the equations of power and relation between current and voltage in AC circuit are essentially the same as those for the DC case. It is customary to measure and specify RMS values for AC quantities. For example, the household line voltage of 220 volt is an RMS value with a peak voltage of Vm equals to root 2V, which is equal to 311 volt. In fact, I or RMS current is the equivalent DC current that would produce the same power loss as the alternating current. It can also be written as P equals to V square upon R, which is equal to IB, since V equals to IR. I'm skipping example 7.1 for you to solve it later, or you may pause the video and solve it right now. 7.3 Representation of AC current and voltage by rotating vectors or phasors. In the previous section, we learned that the current through a resistor is in phase with the AC voltage, but this is not so in the case of an inductor, a capacitor, or a combination of these circuit elements. In order to show phase relationship between voltage and current in an AC circuit, we use the notion of phasors. The analysis of an AC current circuit is facilitated by the use of Phasor diagram. A phasor is a vector which rotates about the origin with an angular speed omega, as shown in figure 7.4. The vertical components of phasors V and I represent the sinusoidally varying quantities V and I. The magnitude of phasors V and I represent the amplitude or the peak values of Vm and Im of these oscillating quantities. Figure 7.4a shows the voltage and current phasors and the relationship at time t1 for the case of an AC source connected to a resistor, that is, corresponding to the circuit shown in figure 7.1. The projection of voltage and current phasors on vertical axis, that is, Vm sin omega t and Im sin omega t, respectively represent the value of voltage and current at that instant. As they rotate with frequency omega, curves in figure 7.4b are generated. From figure 7.4a, we shall see that phasors V and I for the case of a resistor are in the same direction. This is so for all times. This means that the phase angle between the voltage and the current is 0. 7.4 AC voltage applied to an inductor. Figure 7.5 shows an AC source connected to an inductor. Usually, inductors have appreciable resistance in their winding, but we shall assume that this inductor has negligible resistance. Thus, the circuit is purely inductive AC circuit. Thus, the voltage across the source will be V equals to Vm sin omega t. Using the Kirchhoff's loop rule, summation of all the voltages varying with time t is equal to 0, and since there is no resistor in the circuit, V minus L di upon dt equals to 0, where the second term is the self-induced Faraday EMF in the inductor and L is the self-inductance of the inductor. The negative sign follows from the Lenz's law. Combining the equations, we have di upon dt equals to V upon L, which is equal to Vm sin omega t upon L. The equation implies that for time-varying current, the current as a function of time must be as such that its slope di upon dt is sinusoidally varying quantity with the same phase as the source voltage, and an amplitude will be given by Vm upon L. To obtain the current, we integrate di upon dt with respect to time, and we get I equals to minus Vm cos omega t upon omega L plus constant. Integration constant has the same dimension of current and is time independent. Since the source has an EMF which oscillates symmetrically about 0, the current it sustains also oscillates symmetrically about 0, so that no constant or time dependent component of the current exists. Therefore, the integration constant is 0. minus cos omega t is equal to sin omega t minus pi by 2, we have I equals to Im sin omega t minus pi by 2, where Im is equal to Vm upon omega L is the amplitude of the current. The quantity omega L is analogous to the resistance and is called inductive reactance, denoted by XL, where XL is equal to omega L. The amplitude of the current is then Im equals to Vm upon XL. The dimension of inductive reactance is same as that of resistance and its SI unit is ohm. The inductive reactance limits the current in purely inductive circuit in the same way as resistance limits the current in a purely resistive circuit. The inductive reactance is directly proportional to the inductance and to the frequency of the current. The comparison of the equations for source voltage and the current in an inductor shows the current lags the voltage by pi by 2 or 1/4 cycle. Figure 7.6a shows the voltage and the current phasors in the presence of a case at time instant t1. The current phasor is I is pi by 2 behind the voltage phasor V. When rotated the frequency omega counterclockwise, they generate the voltage and AC current given by equation 7.1 and 7.12 respectively as shown in figure 7.6b. We see that the current reaches its maximum value later than the voltage by 1/4 of the time period, that is t by 4 equals to pi by 2 upon omega. You have seen that an inductor has reactance that limits the current similar to resistance in a DC circuit. Does it also consume power like resistance? Let us try to find out. The instantaneous power supplied to the inductor is PL equals to IV, which is equal to Im sin omega t minus pi by 2 into Vm sin omega t. So the average power over a cycle is PL equals to 0, since the average of sin 2 omega t over a complete cycle is 0. Thus, the average power supplied to an inductor over one complete cycle is 0. I am skipping 7.2 for you to solve it later, or you can pause the video and solve it right now. 7.5 AC voltage applied to a capacitor. Figure 7.8 shows an AC source E generating AC voltage V equals to Vm sin omega t connected to a capacitor only, a purely capacitive AC circuit. When a capacitor is connected to a voltage source in a DC circuit, current will flow for a short time required to charge the capacitor. As the charge accumulates on the capacitor plates, the voltage across them increases, opposing the current. That is, a capacitor in a DC circuit will limit or oppose the current as it charges. When a capacitor is fully charged, the current in the circuit falls to 0. When the capacitor is connected to an AC source, as in figure 7.8, it limits or regulates the current, but does not completely prevent the flow of charge. The capacitor is alternately charged and discharged as the current reverses each half cycle. Let Q be the charge on the capacitor at any time t. The instantaneous voltage V across the capacitor is V equals to Q upon C. From the Kirchhoff's loop rule, the voltage across the source and the capacitor are equal, that is, Vm sin omega t equals to Q upon C. To find the current, we use the relation I equals to dq upon dt. I equals to d Vm C sin omega t upon dt, which is equal to omega C Vm cos omega t. Using this relation, I is equal to Im sin omega t plus pi by 2, where the amplitude of oscillating current is Im equals to omega C Vm. We can rewrite that as Im is equal to Vm upon 1 upon omega C. Comparing it to Im equals to Vm upon R for a purely resistive circuit, we can find that 1 upon omega C plays the role of resistance. It is called capacitive reactance and is denoted by Xe. That is, Xe is equal to 1 upon omega C, so that the amplitude of current is Im equals to Vm upon Xc. The dimension of capacitive reactance is same as that of resistance and its SI unit is ohm. The capacitive reactance limits the amplitude of the current in a purely capacitive circuit in the same way as that the resistance limits the current in a purely resistive circuit, but it is inversely proportional to the frequency and the capacitance. In comparison of the equations with the equation of source voltage shows that the current is pi by 2 ahead of the voltage. Figure 7.9a shows the Phasor diagram at an instant t1 where the current phasor I is pi by 2 ahead of the voltage phasor V as they rotate counterclockwise. Figure 7.9b shows the variation of voltage and the current with time. We see that the current reaches its maximum value earlier than the voltage by 1/4 of a period. the instantaneous power supplied to the capacitor is Pc equals to 1 IV, which is equal to Im cos omega t Vm sin omega t, which is equal to Im Vm upon 2 sin 2 omega t. So, as in the case of an inductor, the average power Pc is equal to 0, since sin 2 omega t equals to 0 over a complete cycle. Figure 7.10 explains it in detail. Thus, we see that in case of an inductor, the current lags the voltage by pi by 2, and in case of a capacitor, the current leads the voltage by pi by 2. I am skipping examples 7.3 and 7.4 for you to solve it later, or you may pause the video and solve it right now. Same goes for example 7.4 and 7.5 as well. 7.6 AC voltage applied to the series Lcr circuit. Figure 7.12 shows the series Lcr circuit connected to an AC source E. As usual, we take the voltage of the source to be V equals to Vm sin omega t. If Q is the charge on the capacitor and I the current at time t, we have from Kirchhoff's loop rule that LdI upon dt plus IR plus Q by C is equal to V. So we want to determine the instantaneous current I and its phase relationship to the applied alternating voltage V. We shall solve this problem by two methods. First, we will use the technique of phasors, and in the second method, we will solve the equation analytically to obtain the same dependence of I. 7.6.1 Phasor Diagram Solution. From the circuit shown in figure 7.12, we see that the resistor, inductor and capacitor are in series. Therefore, the AC current in each element at the same time having the same amplitude and phase. Let it be I equals to Im sin omega t plus phi, where phi is the phase difference between the voltage across the source and the current in the circuit. On the basis of what we have learned in the previous sections, we shall construct a phasor diagram for the present case. Let I be the phasor representing the current in the circuit as given by the equation. Further, VL, VR, VC and V represent the voltage across the inductor, resistor, capacitor and the source respectively. From previous section, we know that VR is parallel to I, VC is pi by 2 behind I and VL is pi by 2 ahead of I. VL, VR, VC and I are shown in figure 7.13a with appropriate phase relations. Length of these phasors or amplitude of VR, VC and VL are VRM equals to IMR, VCM is equal to IMXC, VLM is equal to IMXL. The voltage equation for the circuit can be written as VL plus VR plus VC equals to V. The phasor relation, those vertical component, gives the above equation as VL plus VR plus VC is equal to V. This relation is represented in figure 7.13b. Since VC and VL are always along the same line and in opposite direction, they can be combined into a single phasor VC plus VL, which has the magnitude VCM minus VLM. Since V is represented as the hypotenuse of the right triangle whose sides are VR and VC plus VL, the Pythagorean theorem gives Vm square is equal to Vrm square plus VCM minus VLM whole square. Substituting the values of Vrm, VCM and VLM, we get that Im equals to Vm upon under root R squared plus Xc minus XL whole square. By the analogy to the resistance in a circuit, we introduce the impedance in an AC circuit, which is denoted by Z. Im equals to Vm upon Z, where Z is equal to under root of R squared plus Xc minus XL whole square. Since the phasor I is always parallel to the phasor VR, the phase angle phi is the angle between VR and V and can be determined from figure 7.14. Tan phi is equal to VCM minus PLM upon VRM. Using this equation, we have tan phi is equal to Xc minus XL upon R. The equations are graphically shown in figure 7.14. This is called the impedance diagram, which is a right angle triangle with Z as its hypotenuse. The equation gives the amplitude of the current and gives the phase angle. With these equations, it is completely specified. If Xc is greater than XL, phi is positive and the circuit is predominantly capacitive. Consequently, the circuit in the current leads the source voltage. If Xc is less than XL, phi is negative and the circuit is predominantly inductive. Consequently, the circuit in the current lags the source voltage. Figure 0.75 Show the Phasor diagram and variation of V and I with omega t for the cases Xc is greater than XL. Thus, we have obtained the amplitude and phase of current from an Lcr series circuit using the technique of phasors. But this method of analyzing AC circuits suffers from certain disadvantages. First, the phasor diagram says nothing about the initial condition. One can take any arbitrary value of t, say t1 has done throughout this chapter, and draw different phasors for which the relative angle between different phasors. The solution so obtained is called steady state solution. This is not a general solution. Additionally, we do have a transient solution which exists even for v equals to 0. The general solution is sum of the transient solution and the steady state solution. After a sufficiently long time, the effects of the transient solution die out and behavior of the circuit is described by the steady state solution. 7.6.2 Analytical Solution. The voltage equation for the circuit is L di upon dt plus Ri plus Q by C equals to V, which is equal to Vm sin omega t. We know that I is equal to dq upon dt. Therefore, di upon dt is equal to d square q upon dt square. Thus, in terms of q, the voltage equation becomes L d square q upon dt square plus R dq upon dt plus q upon c is equal to Vm sin omega t. This is like the equation for forced damped oscillator in class 11 physics textbook. Let us assume a solution q is equal to qm sin omega t plus theta, so that dq upon dt is equal to qm omega cos omega t plus theta. Substituting the values, we get that qm omega r cos omega t plus xc minus xl sin omega t plus theta is equal to Vm upon sin omega t, where we have used the relation xc is equal to 1 upon omega c and xl is equal to omega l, multiplying and dividing by z equals to under root r square plus xc minus xl whole square. We have qm omega z r upon z cos omega t plus theta xc minus xl upon z sin omega t plus theta equals to Vm sin omega t. Now let r upon z is equal to cos phi and xc minus xl upon z is equal to sin phi, so that phi equals to tan inverse xc minus xl upon r. Substituting this, we get qm omega cos omega t plus theta minus phi is equal to Vm sin omega t. Thus, we can see that Vm equals to qm omega z, which is equal to Imz, where Im is equal to qm omega, and theta minus phi is equal to minus pi by 2, or theta is equal to minus pi by 2 plus phi. Therefore, the current in the circuit is I equals to dq upon dt is equal to qm omega cos omega t plus theta. Thus, the analytical solution for the amplitude and phase of the current in the circuit agrees with that obtained by the technique of phasors. 7.6.3 Resonance. An interesting characteristic of the series RLC circuit is the phenomenon of resonance. The phenomenon of resonance is common using systems that have a tendency to oscillate at a particular frequency. This frequency is called the system's natural frequency. If a system is driven by an energy source at a frequency that is near the natural frequency, the amplitude of oscillation is found to be large. A familiar example of this phenomena is a child on a swing. The swing has natural frequency for swinging back and forth like a pendulum. If the child pulls on the rope at regular intervals and the frequency of the pulse is almost the same as that of frequency of swinging, the amplitude of the swinging will be large. For an RLC circuit driven with voltage of amplitude Vm and frequency omega, we found that the current amplitude is given by Im equals to Vm upon z, which is equal to Vm upon under root r square plus xc minus xl whole square, where xc is equal to 1 upon omega c and xl is equal to omega l. If so, omega is varied, then the particular frequency omega naught xc is equal to xl and the impedance is minimum. This frequency is called the resonant frequency, where xc is equal to xl, or 1 upon omega naught c is equal to omega naught l, or omega naught is equal to 1 upon under root lc. At resonance frequency, the current amplitude is maximum, that is Im is equal to Vm upon r. Figure 7.16 shows the variation of Im with omega in an RLC series circuit with L equals to 1 milli millihenry, C is equal to 1 nanofarad for two values of R, where 1 R is equal to 100 ohm and 2 R is equal to 200 ohm for the source applied. Vm is equal to 100 volt. V0 for this case is 1 upon under root Lc, which is equal to 1 into 10 to the power 6 radian per second. We see that the current amplitude is maximum at resonant frequency. Since Im is equal to Vm upon R at resonance, the current amplitude for the case 1 is twice as that for case 2. The resonant circuits have a variety of applications. For example, in the tuning mechanism of a radio or a TV set, the antenna of the radio accepts the signals from many broadcasting stations. The signals picked up by the antenna acts as a source in the tuning circuit of the radio, so the circuit can be driven at many frequencies. But to hear one particular radio station, we tune the audio. In tuning, we vary the capacitance of a capacitor in the tuning circuit such that the resonant frequency of the circuit becomes nearly equal to the frequency of the radio signal received. When this happens, the amplitude of the current with frequency of the signal of a particular radio station in a circuit is maximum. It is important to note that the resonance phenomenon is exhibited by a circuit only if both L and C are present in the circuit. Only then do the voltages across L and C cancel each other, both being out of phase, and the current amplitude is Vm upon R, the total source voltage appearing across R. This means that we cannot have resonance in a RL or RC circuit. Sharpness of resonance. The amplitude of the current in the series LCR circuit is given by Im equals to Vm upon under root R square plus omega L minus 1 upon omega C whole square, and is maximum when omega is equal to omega naught, which is equal to 1 upon under root Lc. The maximum value is Im max is equal to Vm upon R. For the values of omega other than omega naught, the amplitude of current is less than the maximum value. Suppose we choose a value of omega for which the current amplitude is 1 upon root 2 times its maximum value. At this value, the power dissipated by the circuit becomes half. From the curve in the figure 7.16, we see that there are two such values of omega, say omega 1 and omega 2, one greater than the other smaller than omega naught, and the symmetrical value about omega naught. We may write omega 1 is equal to omega naught plus delta omega, and omega 2 is equal to omega naught minus delta omega. The difference omega 1 minus omega 2 is equal to 2 delta omega is often called bandwidth of the circuit. The quantity omega naught upon 2 delta omega is regarded as the measure of the sharpness of the resonance. The smaller the delta omega, the sharper or narrower is the resonance. To get an expression for delta omega, we note that the current amplitude Im is 1 upon root 2 Im max, for omega 1 is equal to omega naught plus delta omega. Therefore, at omega 1, Im is equal to Vm upon under root R square plus omega 1 L minus 1 upon omega 1 C whole square, which is equal to Im max upon root 2, which is equal to Vm upon R root 2, which may also be written as omega naught plus delta omega L minus 1 upon omega naught plus delta omega C, which is equal to R. Using omega naught square is equal to 1 upon Lc in the second term on the left hand side, we get that delta omega is equal to R upon 2L. The sharpness of resonance is given by omega naught upon 2 delta omega is equal to omega naught L upon R. The ratio omega naught L upon R is also called the quality factor or Q of the circuit, where Q is equal to omega naught L upon R. From the equations, we see that 2 delta omega is equal to omega naught upon Q. So larger is the value of Q, smaller is the value of 2 delta omega or the bandwidth, and the sharper is the resonance. Using omega naught square is equal to 1 upon Lc can be equivalently expressed as Q is equal to 1 upon omega naught Cr. We see from the figure 7.15 that if the resonance is less sharp, not only its maximum current is less, the current is close to the resonance of a larger range delta omega frequencies, and the tuning of the circuit will not be good. So, less sharp is the resonance, less the selectivity of the circuit, or vice versa. We see that if quality factor is large, that is R is low or L is large, the circuit is more selective. I'm skipping example 7.6 for you to solve it later, or you may pause the video and solve it right now. 7.7 Power factor in an AC circuit. We have seen that the voltage V is equal to Vm sin omega t applied to a series RLC circuit drives a current in the voltage circuit given by I equals to Im sin omega t plus phi, where Im is equal to Vm upon Z and phi is equal to tan inverse Xc minus XL upon R. Therefore, the instantaneous power P supplied by the source is P equals to Vi, which is equal to Vm sin omega t into Im sin omega t plus phi. The average power over a cycle is given by the average of the two terms RHS of the equation and is only the second term which is time dependent. Its average is 0. The positive half of the cosine cancels the negative half. Therefore, P is equal to Im Vm cos phi by 2, which is equal to Vm Im cos phi upon 2, which is equal to Vi cos phi. This can also be written as P is equal to I square Z cos phi. So the average power dissipated depends not only on the voltage and current but also on the cosine of the phase angle phi between them. The quantity cos phi is called the power factor. Let us discuss the following cases. Case 1. Resistive circuit. If the circuit contains only pure R, it is called resistive. In that case, phi equals to 0 and cos phi is equal to 1. There is maximum power dissipation. Case 2. Purely inductive or capacitive circuit. If the circuit contains only an inductor or a capacitor, we know that the phase difference between the voltage and the current is pi by 2. Therefore, cos pi is equal to 0. No power is dissipated even though the current is flowing in the circuit. This current is sometimes referred to as wattless current. Case 3. Lcr Circuit. In an Lcr circuit, power dissipated is given by the equation where phi equals to tan inverse Xc minus XL upon R. So, phi may be non-zero in a RL or RC or RCL circuit. Even in such cases, power is dissipated only in the resistor. Case 4. Power dissipated at resonance in Lcr circuit. At resonance, Xc minus XL is equal to 0 and phi is equal to 0. Therefore, cos phi is equal to 1 and P is equal to I square Z is equal to I square R. That is, maximum power is dissipated in a circuit through R at resonance. I am skipping example 7.7 for you to solve it later, or you may pause the video and solve it right now. Example 7.10. At an airport, a person is made to walk through a doorway of a metal detector for security reasons. If she or he is carrying anything made up of metal, the metal detector emits a sound. On what principle does this detector work? Solution. The metal detector works on the principle of resonance in AC circuit. When you walk through the metal detector, you are in fact walking through a coil of many turns. The coil is connected to the capacitor tuned to the circuit is in resonance. When you walk through it with metals in a pocket, the impedance of the circuit changes, resulting in significant change in current in the circuit. This change in current is detected by the electronic circuitry and causes the sound to be emitted as an alarm. 7.8 Lc Oscillations. We know that a capacitor and an inductor can store electrical and magnetic energy respectively. When a capacitor initially charged is connected to an inductor, the charge on the capacitor and the current in the circuit exhibit the phenomena of electrical oscillations similar to the oscillations in mechanical systems. Let a capacitor be charged Qm at t is equal to 0 and connected to an inductor as shown in figure 7.18. The moment the circuit is completed, the charge on the capacitor starts decreasing, giving rise to the current in the circuit. Let Q and I be the charge and current in the circuit at time t. Since di upon dt is positive and the induced EMF in L will have polarity as shown, that is, dB is less than VA. According to the Kirchhoff's loop rule, Q upon C is minus LdI by dt equals to 0, where I is equal to minus dQ upon dt in the present case, as Q decreases and I increases. Therefore, the equation becomes d square q upon dt square plus 1 upon Lcq is equal to 0. The equation has the form of d square x upon dt square plus omega naught square x equals to 0 for a simple harmonic oscillator. The charge on the capacitor therefore oscillates with a natural frequency of omega naught is equal to 1 upon under root Lc and varies sinusoidally with time as q is equal to qm cos omega naught t plus phi, where qm is the maximum value of q and phi is the phase constant. Since q is equal to qm at t equals to 0, we have cos phi equals to 1 or phi equals to 0. Therefore, in the present case, Q is equal to Qm cos omega t, where I is equal to minus d cube upon dt is given by I equals to Im sin omega naught t, where Im is equal to omega naught Qm. Let us now try to visualize how this oscillation takes place in a circuit. Figure 7.19a shows a capacitor with initial charge Qm connected to an ideal inductor. The electrical energy stored in the charged capacitor is UE is equal to 1 by 2 Qm square C. Since there is no current in the circuit, energy in the inductor is 0. Thus, the total energy of LC circuit is U is equal to UE 1 by 2 Qm square upon C. At t is equal to 0, the switch is closed and the capacitor starts to discharge. As the current increases, it sets up a magnetic field in the inductor, and thereby some energy gets stored in the inductor in the form of magnetic energy. UB is equal to 1 by 2 Li square. As the current reaches its maximum value at Im, that is at t is equal to t by 4 as shown in figure 1.9c, the energy is stored in the form of magnetic field UB is equal to 1 by 2 Lim square. You can easily check that the maximum electric energy equals to the maximum magnetic energy. The capacitor now has no charge and hence no energy. The current now starts charging the capacitor as in figure 7.190. This process continues till the capacitor is fully charged at t equals to t by 2. But it is charged with a polarity opposite to its initial state. The whole process thus described will now repeat itself till the system reverts to its original state. Thus, the energy in the system oscillates between the capacitor and the inductor. The LC oscillation is similar to the mechanical oscillation of a block attached to a spring. The lower part of each figure in 7.19 depicts the corresponding stage of a mechanical system. As noted earlier, for a block of mass m oscillating with frequency omega naught, the equation is d square x upon dt square plus omega naught square x is equal to 0, where omega naught is equal to under root k upon m, and k is the spring constant. So x corresponds to q. In case of mechanical system, F is equal to ma is equal to m dv upon dt is equal to m d square x upon dt square for an electrical system. E is equal to minus L di upon dt, which is equal to minus L d square q upon dt square. Comparing these two equations, we see that L is analogous to mass m and L is the measure of resistance to change in the circuit. In case of LC circuit, omega naught is equal to 1 upon under root Lc, and mass of a spring, omega naught is equal to under root k upon m. So, 1 upon c is analogous to k. The constant k is equal to f upon x tells us the external force required to produce a unit displacement, whereas 1 upon c is equal to v upon q tells us the potential difference required to store a unit charge. Table 7.1 gives the analogy between the mechanical and electrical quantities. Note that the above discussion of LC oscillation is not realistic for two reasons. Number 1, every inductor has some resistance. The effect of this resistance is to introduce a damping effect on the charge and current in the circuit, and the oscillations finally die away. Number 2, even if the resistance was 0, the total energy of the system would not remain constant. It is radiated away from the system in the form of electromagnetic waves. In fact, radio waves and TV transmitter depend upon this radiation. I'm skipping example 7.11 for you to solve it later, or you may pause the video and solve it right now. 7.9 Transformers. For many purposes, it is necessary to change or transform an AC voltage from one to another or greater or smaller value. This is done with a device called transformer using the principle of mutual induction. A transformer consists of two sets of coils insulated from each other. They are wound on a soft iron core either on the top or the other as shown in figure 7.20a on the separate limbs of the core. One of the coils is called the primary coil and has NP turns. The other coil is called the secondary coil and has NS turns. Often the primary coil is the input coil and the secondary coil is the output coil of the transformer. When an alternating voltage is applied to the primary, the resulting current produces an alternating magnetic flux which links the secondary and induces an EMF in it. The value of this EMF depends upon the number of turns in the secondary. We consider an ideal transformer in which primary has negligible resistance and all the flux in the core links both the primary and secondary windings. Let phi be the flux in each turn at the core at time t due to current in the primary when voltage Vp is applied to it. Then the induced EMF or voltage Es in the secondary with ns turns is Es is equal to minus ns d phi upon dt. The alternating flux phi also induces an EMF called the back EMF in the primary. This is Ep equals to minus np d phi upon dt. But Ep is equal to Vp. If this were not so, the primary current would be infinite since the primary has zero resistance. If the secondary is an open circuit, the current taken from it is small, then to a good approximation, Es is equal to Vs, where Vs is the voltage across the secondary. Therefore, the equation can be written as Vs is equal to minus ns d phi upon dt and Vp is equal to minus np d phi upon dt. From the equations we have Vs upon Vp is equal to ns upon np. Note that the above relation has been obtained using the three assumptions. Number 1, the primary resistance and current are small. Number 2, same flux links both the primary and the secondary as well as little flux escapes from the core. Number 3, the secondary coil is small. If the transformer is assumed to be 100% efficient, that is no energy losses, the input power is equal to the output power. Since P is equal to IV, IPVP is equal to ISVS. Although some energy is always lost, that is a good approximation since a well-designed transformer may have an efficiency of more than 95%. Combining the equations we have, IP upon IS is equal to Vs upon Vp is equal to Ns upon Np. Since I and V both oscillate with the same frequency as the AC source, the equation also gives the ratio of amplitudes or RMS values of the corresponding quantities. Now we can see how a transformer affects the voltage and current. We have Vs is equal to Ns upon Np into Vp and I is equal to Np upon Ns into Ip. That is, if the secondary coil has greater number of turns than the primary, that is Ns is greater than Np, the voltage is stepped up, that is Vs is greater than Vp. This type of arrangement is called a step-up transformer. However, in this arrangement there is less current in the secondary than in the primary. For example, the primary coil of a transformer has 100 turns and the secondary has 200 turns. Ns upon Np is equal to 2 and Np upon Ns is equal to 1 by 2. Thus, a 220 volt input at 10 ampere will step up to 440 volt output at 5 ampere. If the secondary coil has less turns than the primary, we have a step-down transformer. In this case, Vs is less than Vp and Is is greater than Ip. That is, the voltage is stepped down or reduced and the current is increased. The equations obtained above apply to ideal transformers without any energy losses, but in actual transformers, small energy losses do occur due to following reasons. Number 1. Flux leakage. There is always some flux leakage, that is, not all the flux due to primary passes through the secondary due to poor design of the core or the air gaps in the core. It can be reduced by winding the primary and secondary coils one over the other. Number 2. Resistance of the windings. The wire used for windings has some resistance and so energy is lost due to heat produced by the wire. In high current, low voltage windings, these are minimized by using thick wires. Number 3. Eddy currents. The alternating magnetic flux induces eddy currents in the iron core and causes heating. The effect is reduced by using a laminated core. Number 4. Hysteresis. The magnetization of the core is repeatedly reversed by the alternating magnetic field. The resulting expenditure of energy in the core appears as heat and is kept to minimum by using a magnetic material which has a low hysteresis loss. The large-scale transmission and distribution of electrical energy over long distances is done with the use of transformers. The voltage output of the generator is stepped up so that the current is reduced and consequently the I2R loss is cut down. It is then transmitted over long distances to an area substation near the customers where the voltage is stepped down. It is further stepped down at distributing substations and utility poles before a power supply of 240 volt reaches our homes. So that's it for today. I hope you liked the audiobook. So subscribe to the channel and stay tuned for more updates. Thank you.